Okay, very good. So David, the floor is yours. So this is
Oh.
today David says third and final lecture, and then this will go on for an hour, and thereafter there'll be a question and answer session as well. So David.
Yeah, so maybe what I would do is to break up into two parts and have about 5-10 minutes in between for people to ask questions. I think that's better than continuously trying to go for longer. I think I needed a bit more than 1 hour, maybe 1 hour and 10 minutes, 1 hour and 15 minutes. So maybe two parts with 10 minutes each questions.
Yeah, that's fine. So in between, we want to break for 10 minutes for questions.
Yeah, maybe a 5-minute break and a few minutes for questions. Yeah, that kind of thing.
Sure. You just let me know when you want this break.
Okay. All right. So yesterday we were at the point where we analyzed a particular attack on Bitcoin. So this is the Nakamoto's private attack. And we showed that under this attack, if the adversary power is less than the honest power, then the protocol is safe under this particular attack. So it's robust against this particular attack. And so the question we asked at the end of the lecture yesterday was, what about other attacks? And so 6 years later, people showed that in fact, in some sense, actually not 6 years, but after sort of many years of effort, 10 years of effort, people have showed that in some sense, Nakamoto's attack is kind of like the worst attack. This was not shown by Nakamoto, but shown by a bunch of people. We actually wrote one of the papers in the topic as well. Okay, so basically here's the argument. Okay, so here's the argument of which captures the essence of why the private attack is the worst attack. So you can think of the private attack, if you remember, the private attack is a race between the public blocks, the honest miner, and the adversarial miner, which is trying to grow a fork in private to try to compete with the public longest chain. And so in the attack, the honest miners grow separately and the adversary miner grows separately. However, if you have any attack in general, there may be a mixing of the blocks. So in this example here, you have maybe two chains, but in one chain, the first block is grown by honest miners, white, and the two blocks below that at level 2 and level 3 are grown by adversary miner. Okay, so this is the situation. And so how do we show that in fact any attack, the condition lambda A is less than lambda H is sufficient? Okay, so under the private attack, we have this condition is sufficient. Remember, lambda A is the mining rate or the hash rate of the honest adversary miner, and lambda H is the honest miner. Okay, so the argument roughly goes as follows. I don't have time to go into a lot of details, but roughly goes as follows. Suppose I have any attack and it's successful, okay, and it's successful. Now, the observation, the key observation is the following. If you look at the tree that is generated by any successful attack, then you can look level by level and try to figure out what is the composition of honest versus adversary block. So in this example, at level 1, there is one honest block and one adversary block. At level 2, also one adversary block and one honest block. And at level 3, we have two adversarial blocks, right? So this is the end of this example. Now, you can see that there is, in this example, one combination missing. What is the combination missing? We have two honest block, right? There's no level with two honest block. Am I just missing it in this example, or is this a impossibility? Is it possible that under some attack you could have two honest blocks at the same level? Is that possible? Now let's think about the protocol. The protocol is that the honest miners always mine on the longest chain, right? So therefore, if you have a situation where you have two honest blocks on the same height, then it must be that the honest miner is actually not following the longest chain protocol, because one of these two blocks must be mined first. Suppose this one is mined first. Then the chain extended by one block already. Then this guy, whoever mines this block, should be mining at least at this height, right? Maybe even low, even greater height, greater level, but at least at this, because it's mining on the longest chain. So therefore, it could not be mining here. And so therefore, there could not be a level with two honest blocks. In other words, every level, either you have only one honest block or zero honest block, and the rest must be adversarial block. So therefore, you can now do an argument which basically says the following: if you have any successful attack, if you count the blocks level by level, for every honest block that appears at every level, there must be at least one or more than one matching adversarial block on the same level. Yeah. So therefore, now you can reorganize the blocks on a sample path basis and construct the private attack, which is basically splitting the private block and the honest blocks and two separate forks. And so now you can show that if you have any successful attack, it must be that the private attack itself has already been successful using the same mining times of the block. So this is a so-called sample path argument. It is not a probabilistic argument, okay? And we've already shown that private attack is impossible, with high probability impossible, if lambda A is lambda H, and this shows that any attack is also not successful, okay? So it's a little bit high level, but the rough idea is that there's a matching of blocks, okay? Matching of blocks. And so this is the heart of the argument, and it took people a while to figure it out, but once you figure out, it's actually pretty simple, okay? So this example is to demonstrate that to do a security analysis on a protocol is a non-trivial task, because we are assuming a super powerful adversary which can choose arbitrary strategy, okay? And here, the only limitation on the adversary is really by the mining rate. It cannot generate many, many blocks, okay? And this argument shows that if you have such a constraint, then as long as the mining rate of the adversary is less than the honest block, then the longest chain protocol is safe, okay? All right, so this is the argument. And so therefore one can state a theorem which says that every Bitcoin block, once it has confirmed, is safe with probability of confirmation error goes to zero, exponential in K, as long as lambda A is less than lambda H. We mentioned last time that it's go to zero, but it's basically a law of large number, so concentration, large deviation event. So the probability actually goes to zero exponentially. Just like in coding, the error probably goes to zero. It's a quite similar phenomenon. Okay, all right. So now we prove the safety of Bitcoin. This is a very important result. And the first such result was shown by cryptographers, Agelos Kiaitis and his partners and his collaborators in 2015. That's the first result of this form. Now, okay, so now we show Bitcoin safe, but there's another property that I mentioned yesterday about consensus protocol that is important. Okay, can people put in the chat box if they remember what is the other property other than safety that is important? I mentioned that every consensus protocol, you have to prove two properties, safety and liveness. Yes, liveness means that honest transactions must eventually get into the ledger. So, the thing is that if you only have safety, then it's not very interesting because, a protocol which does nothing is safe, but it's a useless protocol, right? So just looking at safety is not important or not interesting. What you want is a protocol which is both safe and live. So the next question is Bitcoin live? And by that, I mean that honest blocks, okay, will get confirmed into the ledger. So liveness basically means that if you look at the ledger consists of honest and adversarial blocks in general, okay? And I want the fraction of honest blocks to be non-zero so that we have sufficient space to put honest transactions. Because the adversarial block could be all empty, because the adversary may not be interested in putting any transaction in. They may try to censor the whole blockchain. But the honest guy has to eventually, occasionally get blocks into the blockchain at a non-zero rate. That's what liveness means, okay? All right. Now, it doesn't have to that you have to get all honest blocks into the blockchain, okay? That's not the requirement. The requirement is that you get non-zero fraction of blocks. That means the rate at which you put blocks in is non-zero. Now that's good enough because in practice, if an honest block does not get into the blockchain, then the transactions will go back into the buffer and new miners, honest miners will try to push those transactions into the blockchain again. So as long as you have a non-zero rate, then you can push a non-zero rate of transactions into the blockchain. And that's usually people are okay with that in terms of liveness. So now we're going to show liveness. So this is the second result we're going to prove. So the definition is a protocol like Bitcoin is live if a non-zero fraction of the honest blocks are confirmed, or equivalently, if you look at the chain, the fraction of blocks which are honest are non-zero. Okay, so here one has to show two property, okay? One is called chain growth and one is called chain quality. So first, chain growth. So what is chain growth? Chain growth is basically the rate at which the longest chain grows. Okay, that's chain growth. Okay, so chain growth equals the rate at which the longest chain, sorry, typo there, longest chain grows. Okay. All right. Can we have some bounds on this chain growth? Now, this chain growth depends, of course, on the adversarial action, right? But can we have a low bound and upper bound this chain growth? And that turns out to be important to understand the liveness of this protocol. Can anyone give a low bound? Let's call this G. Can anyone give a low bound in chain growth? Okay, so remember notation, okay? We have lambda is the total rate at which blocks are mined, the hash rate, the total. And this lambda is split into lambda A, the adversary rate, and the honest rate, lambda H. And the units of these are blocks per second, okay? Question, what's the low bound on G and what's an upper bound on G? Can anyone give me some reasonable bounds? Lambda H is the low bound, Navin, very good. So Navin, unfortunately is the host and therefore have to listen to these lectures. But I'm glad that you are also paying attention and not checking your emails or something like that. Good. All right. Yeah, so a lower bound is lambda h. A lower bound is lambda h. Because, why? Because, you know, the honest nodes, at least the honest nodes are running on this longest chain, right? So they're working. The adversarial may stop working altogether and not work, but the honest node are always contributing this hash power to the longest chain. So that's low bound. What's an upper bound? Right, the upper bound is lambda. Thank you, Mariam. Okay, so this is the upper bound, which is lambda A plus lambda H. Okay, now we can use that to bound the chain quality. Okay, what's the chain quality? This is the long-term fraction of honest block in the longest chain. Okay. All right. Now so this quantity we have to show that basically if it's live, then this chain quantity should be positive, right? Should be positive. So now we want to show under what condition is this chain quantity positive. Okay, so the chain growth is bounded by these two numbers. Now let's give an upper bound to how many, what's the rate at which okay? How fast can adversarial blocks enter the longest chain? What's an upper bound? So you don't want the adversarial blocks to enter longest chain, a lot of them, because that will push out the honest blocks potentially. Can you give an upper bound? The upper bound is upper bounded by lambda A, right? The adversarial is bind this, right? That's the most you can do. So this is upper bound by lambda A. Okay. Right? Good. Okay. So therefore, the chain quality is lower bounded, is equal to lower bounded by the amount of honest blocks, okay, which is upper bounded, lower bounded by G, the growth rate, the chain growth rate, minus the adversarial rate, lambda A, divided by G. This is the chain quality, right? G is the chain growth. G minus lambda A is what is left over from the adversarial blocks, at least, right? So this is low bound to the chain quality. And this is equal to 1 minus lambda A over G. But G is upper bounded by lambda A plus lambda H. So this is low bounded by 1 minus lambda A over lambda. Did I get this thing wrong correctly? Let's see here. Okay, let's see here. Did I get this thing wrong? Rate at which the adversarial block enter longest chain is upper bounded by lambda A. Chain quality is lower bounded by, let's see, is this correct? Let's see, G minus lambda A. Yes, okay, I think it's correct. Okay, so it's 1 minus lambda A over G. G has a upper bound and a low bound. So I use the low bound to get a low bound on chain quality, right? So therefore, this low bound by lambda A over lambda H. Yes. And so therefore, if lambda A is less than lambda H, then this quantity is positive. Okay. So, lo and behold, the chain quality or the liveness threshold is also lambda A less than lambda H. Exactly the same threshold as safety. So therefore, under the condition lambda A is less than lambda H, the protocol is actually safe and live. Okay. So that's the argument. So therefore, Bitcoin is safe if lambda A is less than lambda H and is live under exactly the same condition. Okay. All right. So that's it. Okay. That's basically the security theorem of Bitcoin. Now, there is one thing which is kind of weird about this whole analysis. So is there any question about the analysis? So at this moment, we have shown that Bitcoin is safe and live. Is it okay? Because now I want to say something which some assumption that I made, which actually I alluded to yesterday on a response to a question, which is I'm assuming that the network delay is 0. Okay. So what are we assuming? We're assuming that if you mine a block, okay, then immediately the block gets propagated to everybody else in the network. Right? That's the assumption, right? But actually, that's a stupid assumption. Because I mentioned in the beginning of the lecture, if you remember, I said one of the big reasons why consensus is a non-trivial problem is because there's network delay. And so if I assume the network is 0, delay 0, it seems like I trivialized the problem already. Because with a 0 delay, everyone can have instantaneously the same view of the problem. Why do you need a protocol at all? It's a trivial problem. Okay. So I have seemingly trivialized the problem to analyze the longest chain protocol. Okay.
Sorry, David, can I ask a question?
Yeah, please.
So I mean, is it possible for any user to like from based on their view of the chain, I mean, or their view of this of the tree, decide at some point that look, they're on the wrong chain, and then try to go back to a better chain that they think has more honest blocks or something like that contains fewer adversarial blocks?
No. First of all, people don't really know which blocks are adversarial and which blocks are honest. There's no labeling, right? Those labelings that I had is only for the purpose of analysis.
No, I agree. But like, suppose that there was some information like that available. Is that possible to do under this protocol?
No. The protocol does not use any information about the content of the block. In fact, it's extremely hard to figure out which blocks are adversarial and which blocks are honest. So it just follows the longest chain. The protocol is very simple. Okay. So now, so here's the real issue, right? The network have delay. So if your nodes are around a network, it's typically communicated through a peer-to-peer layer. And so there will be multiple hops, there will be speed of light delay. So typically it takes like seconds, okay, to get across the network. It's a global network. So, okay, so therefore, what's the problem? Why am I making this assumption of 0 delay? It seems like weird. Okay, so really, I'm not making a 0 delay assumption, but I'm making an assumption that something is very small. Okay. So what is actually assumed to be very small here? Okay. So it is assumed that the delay, okay, is much smaller than something, actually, for this analysis to hold. So what's going on here, right? When there's delay, here's the problem. I'm mining a block on the tip of the longest chain, okay? But maybe by the time I propagate this block, this is no longer the longest chain, and there will be a fork that has already happened because I didn't see the block being propagated. I didn't see the new tip, so I'm mining on an old tip, right? So that is the assumption that we make, that this kind of thing does not happen. In other words, my view of the tip is always updated in some sense. It's always the fresh information. So really, what am I assuming here? I'm assuming the network delay is much more than something. Much more than what? It's much more than the time between the blocks are mined. Exactly. Much more than 10 minutes. Right? So in the case of Nakamoto protocol, it's 10 minutes. Because if the inter-arrival mining time is so slow that it's much longer, the time to generate 2 blocks is much longer than the network delay, which is say 10 seconds. 10 minutes is much longer than 10 seconds. Then what's the chance that when I generate a block, someone else also simultaneously within this 10 seconds also generates a block? It's a very small probability. Okay. So that is what someone alluded to yesterday as natural mining, natural split of the honest power. Nakamoto chose 10 minutes precisely because his estimation of the network delay is a few seconds, or maybe even at most half a minute. So he set this with 10 minutes to make this event of natural forking a very small probability event. Okay? So this guy is really very smart because he has really thought of everything here. 10 minutes is not something that he just randomly picked. Okay? So 10 minutes is really roughly 1 over lambda. So the assumption here is that lambda delta is much less than 1. Okay? So that is the assumption. Not that the delay is 0, you cannot have 0 delay, but it's just that the delay is much less than inter-arrival block mining time. Okay? All right. Now, making this assumption of setting a block every 10 minutes has a very big cost though. Has a very big cost. Okay? What's the big cost? Well, let's think about it. We have to wait. Okay. All right. Before I talk about that, okay, let us now try to now explicitly put in the delta. Okay. Put in the explicit delta and remove this assumption, and then see what happens. Okay, let's do that. So let's assume that the delay bound delta is given, and let's try to analyze this protocol. Okay, when you have a finite delta. In other words, lambda delta is not smaller than 1. Let's see what happens. Okay. So you can put this back into the private chain analysis, and you can actually analyze the race again. Okay. So here's the race. So you have the honest growing, the adversary growing in private. They're trying to compete with each other without a zero network. With a zero network delay, we have a race between lambda A and lambda H, okay? And that gives the condition lambda A is less than lambda H for security, okay? Now, if you have network delay, what will happen? Well, first, the public honest chain may have now forking, okay? Because maybe now you're aggressive and try to choose your mining rate to be 1 block every 1 minute instead of 10 minutes. And now this lambda delta is no longer an insignificant number. And now you get some occasional forking. In other words, that you're not mining on the tip anymore. So in other words, the honest chain growth rate will slow down. Okay. And it's actually quite straightforward to calculate how much it slows down, is precisely lambda h over 1 plus lambda h times delta. Okay. And this is consistent with our original intuition. That is, when lambda h times delta is very small, much less than 1, then this number is now very close to lambda h. But in general, it will be reduced. Now, what about the adversarial? Okay. What happens to the adversarial? Well, the adversarial has the growth rate of lambda a when there is no forking, right? But when there is a positive tau delta, the adversarial may not be affected by this at all. There may not be any forking. Why? Because the adversarial may be one big computer, supercomputer, sitting at one place. You cannot assume that they are decentralized, right? The honors miners are decentralized. They're over the world. But the adversarial could be one big computer sitting in one place. And so lambda a is not affected. And so the private attack condition is now changed to lambda h a greater than lambda h over 1 plus lambda h delta. Okay, so lambda a is less than lambda h for 0 delay, or for lambda delta much less than 1. And now the condition is lambda a is greater than lambda h over 1 plus lambda h over delta. Okay, for the attack. All right, so lambda a is greater than lambda h is for the attack to succeed. And this is in general. Okay, so you can see that this condition is now becoming easier for the adversary to satisfy. And that's the effect of the network delay. All right. Now, there are two questions here. One is, what is the impact of this condition on the design of the protocol? Number two is, well, is this the security threshold actually? So under network delay, is there a worse attack than private attack? Okay. Now that's the more of a interesting question, a theory question. And this is one question that we resolved about last year in a paper in CCS 2020, I think. We showed that in fact, this is not only necessary, but also we have a convert with achievability, which says that if lambda a is less than lambda h over 1 lambda h over delta, then the protocol Bitcoin is actually safe and live. Okay, so this is the correct threshold given by the private attack. Okay, all right. So this is the general result for network delay. Okay, in fact, there was a lot of work done in trying to figure out what the right boundary is under network delay, and there were many papers written. But so basically, we showed that last year, 2 years ago, that the private attack threshold is actually the correct threshold for this problem. Okay, all right. Okay, so now let's see, what time is it right now? What's the time right now? Let's see, 9:07. So I've talked for 37 minutes at this moment, right? Okay, so
We started about a few minutes late, so it's about 32 minutes, I guess, is what.
32 minutes. Okay. All right. So right now we have a theorem. Okay. The theorem is, let me write down the theorem here. Bitcoin is safe and live if lambda A is less than lambda H, okay, 1 plus lambda delta. Sorry, lambda H delta. All right. Okay. So what happens? So we can look at this theorem and say the following. Okay. All right. Okay. So let's just keep track of this theorem. So this is the theorem that we have shown. And this theorem basically shows that when you slow down the chain such that you have 1 block every 10 minutes, okay, then this term is kind of negligible. And so the security threshold becomes lambda A less than lambda H, which means 50% is the threshold. Okay. All right. So now the last topic I want to talk about, okay, the last topic I want to talk about is speeding up Bitcoin. Okay. So that's the last part of the lecture. So let's understand what's going on here. Since I have some time, let me set up the problem. Okay. All right. So first, let's understand why Bitcoin is slow. What's happening here in Bitcoin, right? We have a confirmation rule, which is K deep, right? K deep. As I increase K, the error probability, the confirmation error probability, will become smaller and smaller. So in other words, if I want a very small confirmation probability, then K has to be very large. So for example, for epsilon to be 0.00000006, then K is 50. 50 means I have to wait 500 minutes, more than 8 hours, in order to confirm a transaction. That's pretty long, right? You use that, that's why Bitcoin cannot be really used to buy coffee, because your coffee will become quite cold by the time you confirm. By the time the guy gives you coffee, so that's not good. So you can plot actually this table as a function of epsilon. The latency in minutes goes up to almost 500 minutes at 10 to the minus 6 error probability. Okay, so 500 minutes is K. So latency is K times 1 over lambda, which is the 10 minutes in Bitcoin. Okay, so this is the latency. Notice that this latency, you have to take a hit whether or not there's actually an active attack going on. Even if there's nobody attacking you, you still have to take this latency, because you're always worried that there's a private attack going on that you have not seen. Okay. All right. So, okay, so what do we do? Now we want to improve this latency. Okay, so this is the problem that I want to discuss which is how to improve Bitcoin. So far we've spent our time talking about Bitcoin. Now we want to try to improve Bitcoin. And the first step we're trying to go for some low-hanging fruit, which is maybe to adjust these parameters of Bitcoin. And Bitcoin has very few parameters. The one significant one is this 1 block every 10 minutes. Can I adjust? First of all, can I adjust lambda? Is this a tuning knob that I can adjust by changing the protocol a little bit. How do I change Lambda if I want to? Guys, how do I change Lambda? You remember from yesterday? Yes, by making the puzzle more difficult, in other words, decreasing the threshold, Lambda will increase. If I want to decrease Lambda, sorry, when I want to increase Lambda, that is reduce the mining time, then I want to make the threshold higher. Correct. Increase threshold, Lambda goes up, interarrival time goes down. Good. I'm glad you remember this from yesterday. Very good. So it is certainly possible to change Lambda from 1 block every 10 minutes, maybe to 1 block every 1 minute. Okay. Now that would, if I could increase Lambda 10 times, then I could reduce latency by a factor of 10. And that's really good. Reducing it from 500 minutes to 50 minutes is a big deal. The question is, can that be done? What is there any impact of this on the rest of the system? Okay. So if I could increase Lambda, then I could reduce the latency. Okay. So let's try to remember, right? If I increase Lambda, what will happen to this blockchain? Well, as I mentioned already, there will be forking, right? There will be natural forking. And therefore, the security of this blockchain is actually reduced. So the adversarial fraction, lambda A over lambda, or beta, actually will go down as your mining rate lambda increases. In fact, this mining rate lambda should be normalized by delta. So for a fixed network delay, if I increase lambda, this number will go up. Then the condition for security, okay, will get worse and worse. And so the adversarial fraction required to attack the system goes down from 50% to 0% as lambda increases. So therefore, lambda cannot be changed much, right? You have an estimate for the network delay, and given the estimate for network delay, your mining rate lambda is kind of fixed. All right, so the other suggestion is K, right? So let's do that. Right, so we have this expression. All right, reduce K. No, I don't want to increase K, right, Mariam? Increase K would be a bad idea. Increase K would just increase the confirmation latency. So I want to decrease K. So first I want to decrease lambda, that doesn't work. I want to increase lambda, that doesn't work. Now I want to decrease K, right? But decrease K means that my epsilon will now become larger and larger. Okay, so for a given epsilon, this K is kind of fixed. This K is like the law of large number K. How large do I have in order to, for the given epsilon? So K is also stuck. K is fixed for a given epsilon. Okay. So I'm stuck. Okay. All right. So at this moment, maybe I'll take a 5-minute break. I think at this point, maybe a good time to take a 5-minute break. I don't have a whole lot of time here. So let me take a 5-minute break just to take a breath of fresh air. It's very hot here. I'm sweating, although it's late at night already. And we will come back and explain to you our solution to this problem. We cannot increase K, we cannot reduce K, we cannot increase lambda, but there's something else we can do to improve the latency. Okay? All right, let's take a
Great.
5-minute break.
Sure. Yeah, that's yep, that's fine, David. Yeah, that's good. Yes, it's a good break point, I guess. So
Okay.
We will convene again at 9:55 local time, which is probably 9:25.
9:25. 9:25. Thank you.
Perfect.
Hello?
Yeah, David, shall we resume?
Yeah.
All right.
Okay. All right. So we are to the last part of the lecture. And so this is actually a paper we wrote a few years back. It was our first paper in blockchain that we called a protocol Prism. And we presented it at ACM CCS 2019. Okay, so to understand how to solve this latency problem, we went back to first principle to try to understand what Bitcoin is actually doing. And it turns out that Bitcoin actually has a block in Bitcoin has 2 rows. The first row is proposing a block, proposing transactions. This is pretty standard. You mine a block, you propose transaction, and you put it on the chain. But the second row is actually a row of voting. What does that mean? So a block gets into the blockchain. It proposes transactions. That's the first row. However, when a block gets into blockchain, it actually implicitly is doing something in addition to proposing transaction, which is that it is voting for the block, a block which is appearing as an ancestor on the blockchain. So for example, when this block is mined, okay, what it is saying is that, hey, I'm mining on top of this block. That means I'm voting for this block. I believe that this block above me should remain in the blockchain and should become part of the ledger eventually. And when this guy shows up, okay, he's voting for this guy and he's also voting for this guy. So K-deep confirmation rule basically means, hey, let's confirm a block, not when you only get 1 or 2 votes, but when you get 10, 20 votes or 50 votes. So what's going on here is the following. In some sense, every time a block is mined, I'm like sampling a vote from the population of honest miner on the longest chain. The adversary is also trying to sample its own miners, the bad miners. And if I only sample a few guys, the adversary may get lucky and quickly get a sufficient number of votes to overcome me. But if I sample over many times, then I'm getting the statistical average, okay? And if I have more mining power, I will get more votes. Or equivalently, I will get a fixed number of votes at a faster time, K votes in a faster time. So basically, it is a very simple but intelligent voting mechanism. But because voting and mining and proposing is intermingled, it makes it harder for us to try to speed up this voting process. And so our idea was that we should try to decompose these 2 rows, separate them, so that we can speed up or scale up the voting process. So the whole problem of latency in Bitcoin is that 1 vote comes every 10 minutes. And you have to get, say, 10, 20, 30, 40, 50 votes. That takes a long time. So Nakamoto was very clever in designing a very secure protocol, but the performance-wise is very bad. And no, And so our goal was trying to speed up this voting process and through a redesign of Bitcoin. And so our idea was that we should try to deconstruct Bitcoin into two types of blocks, each of which have their own separate role. One role is for proposing, which we call proposer blocks, and the other one is for voting. Okay? So, and then once we deconstruct that, then we could try to think of clever methods of scaling up, speeding up the voting process to reduce the confirmation time. Okay? All right. So we have Bitcoin, which is a single type of blocks, every block proposed and vote. We separate out into two types of blocks. Okay? So now, effectively, I'm running two separate proof of work lottery. Okay? One for proposal blocks and one for voter blocks. Okay? And the proposal blocks receive votes from the voter blocks. So what does it mean by this arrow? Arrow basically means that you include the hash of the block. Okay. All right, I completely forgot what I'm going to say. Okay, well, got it. Okay, so the voting block is voting for the proposal block means that it will include the hash of the proposal block. Okay, so the idea is that if you decompose it this way, then it doesn't seem that we have increased the confirmation time, right? Or reduced the confirmation time, because the voting block are following a chain, a longest chain actually. And this itself has to be very slow. We know that. So this doesn't seem to improve anything. It seems to only make things more complicated, which is not our intention. But once you realize that you can separate out the row, then instead of mining one voter chain, you can now mine many, many voting chains in parallel. Okay? And all of them can simultaneously vote for a proposal block. Okay? So that is the general idea of speeding up the voting process, where each voting chain follows a longest chain protocol. And so each voting chain, the blocks are mined very slowly to make sure that it's secure, it doesn't have any forking problem. However, now I have many chains growing in parallel. And so now I can speed up the voting process by having many, many parallel chains voting at pretty much the same time. Okay, so this is the high level idea. So let's go into a little bit more detail. So first of all, to make this idea work, I have to be able to run many parallel proof of work lottery simultaneously. And fortunately, this construction of running parallel proof of work lottery is already invented by cryptographers, so-called 2-for-1 mining. Okay, so I'll go a little bit more detail on how that works. Okay, but let's assume that we now have a mechanism of running many parallel proof of work lottery. So in some sense, you're simultaneously competing for blocks on all of these chains. So if, for example, suppose there are 1,000 voting chains and there's one proposal blocks. So there's now 1,001 proof of work lottery. And the adversary and honest is competing separately in each of these lottery, according to the mining power, okay? All right, so each of these chains will be safe and live if the adversary power is less than the honest power. Okay. Now here's the strategy. So first, blocks get proposed across different levels. Okay. Now, each voting tree will now vote for the first seen proposal block at each level. Let's not use the word height. To be consistent with earlier, let's call it level. Okay, so here at say level 2, there's a proposal block showing up. Okay. And then all the voting chain that see this block and have not voted for it yet at that level will now vote for this block. So very quickly, you will get quite a lot of votes. If there are 1,000 chains, very quickly, you will get, a few hundred votes. And a vote only counts if it's voting from the longest chain of their respective voting chain. Okay. And for each level, we simply choose the proposal block with the most votes. So that's it. Okay. All right. So just a few words about how you can run all these parallel proof of work lottery. Okay. So actually, it's a very nice trick to do. So you remember that the hash puzzle is something like you evaluate a hash function and put a nonce there, and then some other stuff here. It's less than a threshold. Right? This is the puzzle. That's right. Well, how can you generate 1,001 different puzzles? So suppose there are 1,000 chains here and one proposal tree here. How do you generate 1,001 puzzle from one puzzle? Well, you simply divide your line. So you can think of a puzzle is by setting a threshold. And if you are here, this is the interval from say 0 to 2 to the 256, because there are 256 bits in the hash function. So this is the interval, and you have a very small threshold with many zeros, 80 zeros. And only if you fall into this zero, you get a block. This is the Bitcoin puzzle. Okay. But now I can replicate these intervals and extend them to 1,001 such interval. And what I'm saying is that, okay, if you fall into this threshold, you get a proposal block. But if you fall into any of these thresholds in Bitcoin, you get nothing. But in this protocol Prism, you will enter one of these voting chains. So that's how you can run 1,001 parallel lottery using one hash function computation. Okay, so this is the basic cryptographical mechanism to allow us to do this parallel mining. Okay, so the theorems we proved, which we'll not discuss the proof, but just to state it, is the following. Okay, so Prism can achieve safety and liveness against an adversary with less than 50% of the total hash power. So this is the same statement as Bitcoin. So this statement basically says Prism inherits the security properties of Bitcoin. We didn't lose anything. However, in terms of latency, we can show the following. Okay. We can now confirm transactions with a latency which is independent of epsilon. Okay, independent of epsilon. So now we don't have to wait until something is k block deep. Instead, we can make the confirmation error as small as we wish by making the number of voting chains large. Okay, so instead of waiting a long time, we have increased the number of voting chains to get many votes in parallel. So we're getting the law of large numbers through a different way. Okay, all right, so let's see how that works. All right, okay, so here's a comparison between Bitcoin on the left-hand side and Prism on the right-hand side. In Prism, in Bitcoin, you have to wait until many block deep in order to get a very small confirmation error. So in this example, epsilon k is 0.001. Then using Nakamoto's table, you can show that you need the confirmation rule to be k equals 24. Okay, so k equals 24 is to make this error probably small. Now let's look at what happens in Prism. So why do we want that? We want that so that if you have another block proposed at the same level in Bitcoin, then it's very hard for the adversary to get that many votes within the same time frame, because the adversary has less mining power. Okay, so there's a law of large number over time. Law of large number over time. Now here, the same situation is you get a lot of votes, but now you are averaging over many chains. Okay. Now the question is, for each of those chains, do I have to wait until each block is 24 deep? Or can I wait until it's much shallower, much shorter, so that I can improve my latency? Okay, let's do the calculation. So I want to say that, okay, suppose I have 1,000 votes already on a public block. Okay, 1,000 votes on a public block. I want to know that the adversary cannot mine a block in private and simultaneously fork off, have a private attack, okay, on a sufficient number of these voting chains to change the vote from voting on this block to voting on this block. So this is the analogy of the private attack, right? So the private attack here is basically you don't want votes to be on a private block. Here, the analogous thing is that this competing proposal block in private may, a adversary may already be branching off some of these chains in order to put votes on this guy and therefore change the votes on this guy. Okay, so the question is, how long should I have to wait until I'm quite sure that among the 1,000 votes, more than 500 cannot change over to the adversary, right? That is the analogy of the private attack. Okay. So
sorry, David, there's a question
yeah.
in the chat, if you can just address.
Oh yeah, sorry about that. Does the process of voting happens independent at each miner? Okay, let's understand what this statement means here. So can you, okay, maybe you can speak up because I didn't quite understand this question. I'm trying to figure out what this question means.
All that I'm asking is, does each node maintain their own versions of the voter trees also? That's what is meant by. So,
yeah, so in a Bitcoin, right? Each miner maintains the view of the entire block tree. In this case, it's one tree in the Bitcoin, right? In the case of Prism, it's going to maintain 1,001 block trees. One for the proposal blocks, and one for the one for each one of the voting trees. So each miner will maintain 1,001 trees.
sure. Yeah. Thank you.
Okay. Is that good? All right. Okay. So remember, very importantly, only votes on the longest chain of each of the voting tree counts as real vote. So the adversarial attack is that it will try to build private fork to try to subvert a fraction of these 1,000 votes, so that a proposal block that has already been confirmed with 1,000 votes became deconfirmed because this other competing block can obtain more than 500 votes. Okay, so, well, so you're asked a question, okay, which is, well, instead of having, I want my confirmation error to be no more than 0.001. So therefore, I should ask the question, what is the probability that more than 500 votes will get reverted? Okay, how long should I wait for each one of them to be deconfirmed in order that the probability more than 500 votes are reverted is less than 0.001? Okay, and it turns out that you don't have to wait long. As long as the probability of deconfirmation on each of the longest chain, or the probability of forking on each of the longest chain, is no more than 0.45, which is a very big error probability, then because you have 1,000 voting chain, the chance that you get 500 votes reverted is very small. Because on the average, you only get 450 votes reverted. Because the chance of reverting a vote by having a longer chain on this chain is 0.25. You only have to wait very short, 1 or 2 blocks, and you get 0.45, and you're happy. Because all you care about is you don't want 500 votes reverted, but having 40.45 will guarantee you with high probability that this event won't happen. Okay. All right. I don't think I'm doing very well explaining this point here. So is there any question that will really help me to elaborate on this point? So think about it. Each chain is trying to generate a vote. Okay. So in public, 1,000 chain already have voted for the candidate they want, which is this proposal block. The adversary is trying to grow a block in private and trying to fork off more than 500 of these 1,000 chains in order to be able to get a block with more than 500 votes. Because if it succeeds in generating a block with more than 500 votes, then according to the protocol, then this block will be confirmed instead. So there's a safety attack. Okay. What I'm trying to argue is that I don't need to make each one of these chains very reliable. As long as the probability of not changing is decently less than 0.5, then I can guarantee that the probability of having 500 votes reverted is very small. So in other words, instead of having a law of large number over time, I have a law of large number over the voting chains. Okay. And so now I don't have to wait for time. I just have to have a lot of voting chains, which is part of my design. I can set M to be 1,000. Okay. So that basically allows us to have fast confirmation. You can think of this as like, you have a bag of each chain is like a classifier. They're very weak classifier, but together, working together, they form a very strong classifier. Okay. All right. So that allows us to do a fast confirmation. We actually implemented this protocol. So we could get confirmation typically of the order of 20, 30 seconds. instead of 10 minutes. So it's much faster confirmation time. Okay, so I feel like at this moment we're at what, 10:20, right? So instead of trying to cram more material, I think at this point I want to stop and sort of take any questions to allow for 10 minutes of questioning, because I know that after 10:30 there must be another event happening at the workshop. Is it good,
Right,
Navin?
yeah. Yes, that's correct. I think
I still have a bunch of slides, but let me just pause here and take questions.
Satyajit, I think the next event on the agenda is at 10:30 or 10:40.
It's 10:30. Yeah.
Okay. So I guess, yeah, we should then start wrapping things up. So
Okay,
we'll open
good.
the floor for questions at this stage. So these talks are being recorded, Satyajit, and will it be available for participants to view later?
Yes, yes. So it's not, we are not able to download them, but we'll try to do something and download the videos.
The
and
size is too
upload.
large.
No, we don't have permission, so we can see on that Zoom cloud, but
Yeah, let me do a little bit investigation, the strategy to figure out whether it's possible to download. I'll ask some of my students who was my TA, and they may know.
yeah.
But typically this recording is used for Stanford lectures. And so they don't want people to download because they have some privacy issue for Stanford students. So that's the reason why it may be difficult to download. But of course, you can always do a screen capture and figure out something there. But that is the worst case. So let me check it a little bit with my students to see if there are any tricks we can play here.
Sure.
Questions for David? Let me ask you this, David, and just to get things going. Oh, well, there is a question here. There is like,
every node should, okay, the question is, by Mariam, is in this protocol, every node should generate 1001 block at each time. Doesn't it lower the speed of the protocol? No. No, why would it slow the speed of the protocol? I didn't quite understand that. In fact, we're making the puzzle easier in some sense to generate many blocks so the protocol is speed up. Remember, the computation power of the computational work of the miners are all in solving the puzzle. Dealing with 1000 blocks is no big deal, is from my computational point of view. Just having many more blocks in the memory, more blocks to deal with is not a big deal at all. It's negligible computational load compared to manage this data structures, completely negligible compared to the mining, which is all the work.
so my question was, sorry, there's another one. Is Prism better than Bitcoin in terms of all metrics? This is from Abul Fazal.
Abul Fazal, is Prism better than Bitcoin in terms of all metrics? Let's see. Yeah, I think so. Yeah. Mm-hmm. Yeah, I mean, of course, Prism has not been implemented. There is no version of Prism that I know of that is implemented on a global scale. So it's a bit hard to, so from a theoretical point of view, certainly Prism has all the benefits of Bitcoin and more. From a practical point of view, it's hard to make the comparison because Bitcoin has been around for 12 years and it's running in the wild for so long. And Prism has this exposure or experience. So it's hard to compare from a practical point of view. But from a theoretical point of view, and we have also built prototypes of Prism, they seem to work quite well. So I think Yeah, I think it's very competitive to Bitcoin and have latency advantages. Is it possible to have multiple honest proposal blocks at the same level? Yes. Yes, so that is my next slide. Yes. So when I stated the theorem, what I stated was that in the normal path, when there is no attack on the protocol, the latency is speed up. In Bitcoin, even when there's no attack, you have to wait K deep. However, when there's an attack, such as here, when there are multiple proposal blocks, when there are multiple proposal block, it means that the adversary must be proposing one block, right? Because we know that two honest blocks should not appear on the same level when I set the mining rate to be adequately slow. So this situation must be achieved by an explicit open attack. And so the attacker could try to arrange things so that one block has 499 votes, the other has 501 votes. So it's a near tie. So now the law of large number argument doesn't work anymore because now we're at microscopic scale. So now, in this case, we really have to wait until each chain is very deep in order to make sure that each of these votes are very solid so that we can confirm. But this is all visible because the protocol knows that the number of votes are very close together. And now at this point, it has no choice but to wait longer to make sure that each vote is very deep in their respective chain so that I can confirm. So now we fall back to Bitcoin level latency. But this is only under an explicit attack. So in the normal path, Prism with very fast latency, under explicit attack, it may have Bitcoin latency. Bitcoin, whether it's under attack or no attack, it always have slow latency. Is that clear, Lalita? That's a very good question.
Yeah. Thank you. Yeah, it's clear.
All this is contained in the paper, it's described in the paper.
So you have implemented Prism. Are there implementations that are actually available?
Yeah, so we implemented on Rust. So in fact, we had a performance. This is in the paper that we wrote. And we have some performance numbers for Prism. And yes, we have a GitHub site for this. And if you're interested, if people are interested, they can play around with it. Yes. You can find it in this paper. But with Lei Yang at MIT, we have a collaboration. We built this Prism a few years ago. I know of some projects which tries to implement Prism. I'm not completely sure what the status of those projects are.
Okay, so I think we should then wrap it up here. I don't see any further questions, but I think any other questions perhaps can be taken now, like offline. They can send emails to David or something like that.
Yeah, maybe I can give 30 seconds to say a few concluding remarks. So
absolutely. In fact, you can keep the Zoom going because anyway, the other talks are going to be on a different platform. If in case people are interested to stay here, that's also feasible, right?
All right.
But yeah.
No, yeah, I'm not going to stay very long anyway. But yeah, if people are interested in asking me questions, but I want to say a few words, which is, the funny thing is that blockchain seems like totally different area than information theory, right? It seems like not really related. But the funny thing about this problem is really how to use law of large numbers in a clever way in order to improve the performance of protocols. You just think about it. Nakamoto used law of large number in a particular way, and it works, but the latency is long. And we use law of large number in a different way in order to get the same law of large number effect by using it much faster, by in some sense averaging over space rather than over time. And this is something that information theorists sort of is probably the only type of people who think about is really how to use the law of large numbers appropriately. Building multiple antenna system to do a diversity. as opposed to diversity over time, where you have to wait a long time for the diversity. So all this thinking is kind of in the back of our mind, sort of helping us to solve this problem. Why it has to wait like 10 years until the solution shows up. I think there's a reason for that. And I think that's sort of the information theory training of understanding and using the law of large numbers. It's kind of weird, kind of interesting, I thought. I have a non-technical question. Do we expect any time in the future a revolutionary book like your wireless communication book on blockchain technology? Yeah, I think this area deserves a book. I don't know if it's ready yet because the technology is still evolving very fast. Many new ideas. So maybe it's a little bit too early for something as stable as a book. I think wireless, it took us quite a few years to wait a few years until we decide to write the book when the thing becomes a bit more stable. And I think we kind of picked a good time because we kind of capture a moment of the field where there are a lot of new ideas, but it sort of stabilizes and it became useful for the next decade, I think. So I think that time will come, but it has not really come yet. That's my feeling.
So let me now go ahead and thank David for an excellent tutorial. It was lucid and very clearly presented. So he has clearly had prior experience with this. And like, thanks for staying up late as well to accommodate the time difference.
Yeah.
And it's a bit unfortunate that we couldn't have you here in person.
Yeah. So let's hope that we have another chance to visit.
Yes.
I was looking forward to hiking in the mountains, but yes, that was Satterjee's temptation for me to participate in the event in the first place. And now I get to sit in my. Now I get to sit in my garage.
I hope that I also wish that everybody would come here and we'll organize something, such a nice gathering soon. Yeah.
Great. All right.
Thank you, David.
Yeah. So, oh wow, PV Kuma's here. Hi. Cool.
Yeah, Vijay has been attending your lectures throughout.
Oh wow, great. How are you, Vijay? Good. Okay, so I guess maybe I should not stay here because everyone should go back to the proceedings. I don't want to distract people from the main flow of the program. So thank you so much, everybody, and thanks again for inviting me here. So I think I will sign off from here and take a break from this heat.
All the best.
Bye.
Thanks, Navin.
Bye, everybody.
Thank you.